I know you are expecting Dr. Dong, but I'm your substitute teacher today. Right. So she's gone for the conference. So while she's gone, I will cover the class. So only for this week. So here's my name. So my office. My office hour, 7th period. So right up this class. To give you a better idea, I was born in South Korea. This is my name in Korean. So they write the last name first. So in Korean language, this is my name. And also when I was born, they also registered my name in Chinese character at the same time. So this is a Chinese version of my name. I try to some time to explain what it means. So last name, Kim, in the word itself is gold. Okay, so it's gold, it's expensive. And the first name Nam is, have you heard about the Vietnam? That same Nam, it's south. Ho, I still try to understand why my parents put that name on me, but that's basically a tiger. So literally, if you interpret it, my name is Golden Southern Tiger. But don't worry about it. I will not bite you. My office hour in A building, and the office hour is right after this class. When I ask a student's name, they often say their name very fast. Why? Because the name is so familiar to them, but I'm here first time, right? So if you say your name so fast, there is no way I can remember your name. That's the thing. The reason that I explain extra time on my name is, in this way, probably many of you, more of you, can remember my name at the same time. So that's the idea. Now we go back to class. So did Dr. Dong talk about the statically indeterminate system last class? She did. Statically indeterminate system. Can anybody tell me what the statically indeterminate system is?
There'd be more unknowns than equations to solve them.
More unknowns than equations. That's a mathematical definition. Anybody else? I mean, that's correct. Anybody else? You are ready to graduate mechanical or aerospace engineering, and I'll be really disappointed if you don't know what is the statically indeterminate system is. Anybody knows what is the statically indeterminate system? So mechanical engineering definition is you have a more constraint than freedom. You have a more constraint than freedom. In the static class, in statically indeterminate system, you cannot solve the problem by force equilibrium, right? So you need to consider extra deformation to satisfy the constraint to solve the member forces. So it makes your life more complicated. Did Dr. Dong talk about it become easier in the finite element if your structure is indeterminate? Did she talk about it? Okay, it is easier because you eliminate more rows and columns as you have constraint. But more fundamentally, why engineer like statically indeterminate systems? Why we bother by making our structure system to be indeterminate? One, to make problem more complicated, so you cannot solve it properly. Two, there must be some reason that engineers prefer statically indeterminate system. Anybody? I'm not interested in you guys to memorize the equation and then plug in numbers to solve the problem. It allows you to move things. While making statically indeterminate, it allows not to move it. You have a more constraint, right? You have a more constraint, so it's more stable.
There's a higher factor of safety.
Factor of safety depends on the level of stress. So I can make a statically indeterminate system with a factor of safety 1, or I can make a statically determinate system with a safety factor 4 that normally do in the civil engineering. In the mechanical and aerospace, we live in the safety factor of 1.5, but in different disciplines they can go 4 or 5. But that can be controlled by changing the member size. Anybody else?
Just overall structural stability?
Stability. Why statically indeterminate system more stable?
More constraining?
More constrained, yes. So imagine if you have a statically determinate system, and if one member fails, then what happens? The entire system collapses, right? And you don't want that happen while you are flying the airplane, right? So the statically indeterminate system, even if one member fails, other members still can satisfy the equilibrium and they can hold the structural integrity while you're flying. That's why the airplane has 2 engines. I've seen several times the one engine blow up. The airplane does not fall down from the sky. They can still land it nearby the airport. That's the indeterminate. So these are all related to how much I want to make my system to be stable, even if something goes wrong. So in that sense, a statically indeterminate system is very important. What we want to study today is, you learn the one-dimensional bar element last class. The one-dimensional bar, right? So you can satisfy equilibrium, you can calculate the displacement, etc. But this is the real structure. They are not one-dimensional bar. They are somewhere in the space. They are different orientation, they are different angles. They are connected, multiple of them. Bridge. Olympic Stadium. How you solve it? The safety of the Olympic Stadium using finite element. So that the picture on the upper right corner is the finite element stress analysis of the stadium. Or we can go to the Eiffel Tower. How many trusses there? I don't know, I cannot count it, but that's how it is, and you can actually run the simulation to see what's the maximum stress, how much deflection you'll have, when the earthquake happens, whether your tower will be safe or not, how much the safety margin or safety factor you have. So that's what you want to do. So it's completely new. It's called the plane truss. Okay, now I erase my name. So topic today is section 1.3, plane truss. So before we start class, are there any questions? Any questions? So we start with a no question class. All right. I have a one-dimensional bar here, right? I have one-dimensional bar, and I can apply force in this direction and force in that direction, right? And you know how to solve it, right? Say yes. Yes. Okay. Now, let's say, what will happen if I rotate it? Can you solve it? How can you solve it? That's the topic of today. So if you know how to solve inclined bar, we call it truss, then we are done, right? How do you solve it? You solve it very carefully. Right? Did this bar change from here to there? No, mechanically they are the same bar. What's the difference? What's the difference? Yes.
In this version, the bar is not just on a singular axis; it's passing through a plane.
So axis. What defines the axis? Coordinate system. The only change from this bar to this truss is a coordinate change. Right? Did God create a coordinate system? No. Some of the mathematicians developed a coordinate system. Right? So the physical behavior of this bar should be identical whether it is horizontal or it is inclined. Only matter is the coordinate system. Now, then, where is your coordinate system? It's your freedom, right? You choose somewhere at your x, y, z coordinate, you solve the problem, right? But what if I sit on it? I sit on the bar, and the bar rotates. What do I see? Nothing. Nothing changed, right? So if I sit on the bar, no matter where your direction is, it doesn't matter because as far as I'm concerned, I see the same one-dimensional bar. So that's what we are trying to do today. We are not developing new system or new physics or new element. It's basically the same element, but we are looking at from different coordinates. So that's a plane truss. It is basically a 2D bar. And then they are connected by, the joint is important, pin joint. So I will take an example. Let's say there is a vertical one, and there is inclined one, and there is inclined one. Let's say you have these 3 bars. Sorry about my handwriting, and they are pin joint with the ground. And then let's say you apply, they are pin joint at the center here, and you apply force F. So 3 bars in plane, they are connected by pin joint, and then there is a force at the connecting point. So before we go further, I want to ask you a question about 2 force member. So please define what is 2 force member. Anybody? It's supposed to be opposite direction. You asking me a question and I'm supposed to answer. But now it tends to be I ask a question and then waiting for your answer. But anybody can define what 2 force member is?
It's a member connected by pin joints on each side and nothing acting.
That's
Member.
okay. What happens? Yes, geometrically, yes. Any other definitions?
Basically, just a bar with forces, where there are forces located only at the ends, like the joints.
At the end of joint, yes, close. 85% close. Anybody else? So if you have a bar, you force apply that at both ends, and
You replace that bar with just a force that will act the same.
in what direction?
The opposite direction.
As I said, it's basically a member and only tension and compression. No
Axial
force.
direction, yes. The force is only applicable on axial direction. Doesn't matter which direction that you are, the force is always along the axial direction. If you are not in pin joint, if you have a clamped or welded joint, then there is a possibility the force direction may not be different from your axial direction, right? But in pin joint, if you apply force in different direction, it will rotate it, it will make it flat. That's 2 force members. So that's the bottom line of this one. Okay. So it is a 2 force member. So let's draw one of the member. Let's see this one. Let's draw this one separately. So I have this. And I choose the node 1 to the left, node 2 on the right. It doesn't matter actually, but let's choose this one. And then there is a coordinate system, right? So I have a coordinate system, X and Y. Coordinate system. This coordinate system is fixed. It's so-called global coordinate system. Node 1. In what directions the node 1 can move? In what directions node 1 can move? In plane, every point can move either horizontally or vertically, right? So node 1 has 2 degrees of freedom. The main difference between 1D and 2D model is 1D model, even if it's drawn on the plane, it's not allowed to move up and down. We only restrict its motion only in horizontal directions, right? But now, since we are talking about plane truss, every node can move in either X and Y directions. All right, so that's possible. I call it U1, V1. V is vertical, so U is horizontal, V is vertical. The same reason, U2 and V2. So this U1, V1, U2, V2 are so-called degrees of freedom written in global coordinates. Now we decided to sit on the truss, right? So let's sit on the truss, meaning, in my perspective, this is my coordinate system. This is my highway. Okay? So this is, I call it X bar and Y bar. So this is, the bar means local. This is your global. Any questions so far? Yes.
Why you didn't consider your global at with your coordinate system B1? No, they point to the same direction.
Yes, you can choose any arbitrary coordinate that you want, but at least you have a one coordinate, right? And then that it's easier to express everything with respect to that coordinate. Okay, but the global does not mean the D global. The global means it's just something that fixed and everybody want to look back. Okay, so there is, you don't have a multiple global. You have only one global. You can have a multiple locals. Okay, my coordinate, your coordinate, and her coordinates will be all different. Doesn't matter as long as I have a one reference frame, so-called global coordinates. I can always come back to the global coordinates. But that local and global must have some relations, right? You cannot be just arbitrary. So the way in the plane truss, I define my relation between my local to global by angle phi. So angle phi defines how much my local rotate with respect to global. Phi, angle. No, it's not just the angle. It's a very specific angle, right? So how I define my local coordinate will trick you at the exam, always. So just to make sure that this one, you need to just carve on your bone. This is the angle phi between plus x. This is your global positive x coordinate and plus x bar. So in one-dimensional bar, did we use the convention that always node 1 is on the left node, node 2 is on the right node, right? Why we do that? Because in that way, my global coordinate and my local coordinates are parallel, so I don't have to worry about that. But from now on, you can choose the node on the right as 1, node on the left to be 2. It's your freedom. You can choose arbitrary node sequence as long as your angle is defined between positive global x-axis to the positive local axis. So right now, I implicitly define here node 1 is my first node, node 2 is my second node, right? But it's perfectly fine. You can define node 2 is first node and node 1 is the second node. What will be the difference then between the first definition 1, 2 versus 2, 1? What's the difference? Sign is going to be different, but how do you know that the sign will be changed? The sign is always defined as positive x to the positive x bar. So that's how we define local coordinate. Local coordinate is always starting from first node to the second. If I change my first node to be 2, second node to be 1, then my local axis will go this direction. Then angle will be 180 degree plus pi. Make sense? So from now on, we release that restriction that there is no left node and right node. That is, you can pick arbitrary node sequence, but you need to show what is your first definition of the node and the second definition of the node. And that definition will tell you what angle that you will have. That angle is always in the positive local x coordinate. Any questions? All right, then in that coordinate, if I look from that coordinate, this is my displacement, isn't it? U1 bar and V1 bar. Here same, U2 bar and V2 bar. Again, we have a 4 displacement. U1 bar, V1 bar, U2 bar, V2 bar. So question to you, if I know U1 and V1, can you calculate what is a U1 bar and V1 bar? If I know U2 and V2, can you calculate the U2 bar and V2 bar? Can I ask you that question in the exam? So that's all about this class. If I know my displacement, either global or local, then I can calculate something else using just the angle phi. It's called the direction cosines. That's what we learned in the class. All right. So now we go back to the local coordinate. So I would say same as 1D bar in local coordinate. Again, the physics does not change, so that EA over L 1, negative 1, negative 1, 1, U1 bar, V1 bar equal F1 x bar, F2 x bar. So let's go back. What is F1 bar, F2 bar? So this is F1 x bar. This is force F2 x bar in the bar directions, right? So this is a 2 force member, so the force has to be always along the axial direction. And this equation is written as K E bar Q bar equal F bar in matrix notations. We are done. We are done. The only problem is we have 3 elements, right? In the figure of top, we have 3 elements. One is in this direction, the other that direction, and the other. They all have a different local coordinate. Do you agree? Element 1 to 3 will have a different local coordinates, right? And now we write it as U1 bar, U2 bar, U1 bar, U2 bar for the element 2, U1 bar, U2 bar for element 3. All elements will have a different local coordinate system. How do you solve it? To solve it, you need to assemble it, right? To solve the matrix equation, you need to assemble them. But when you try to assemble it, element 1 says, oh no, my U2 bar is different from your U2 bar. My U3 bar is different from your U3 bar. How can I assemble it? That's the problem comes in. Because everything is defined individual element-wise. And when it comes to assembly, now it's a problem. So you cannot assemble it. You cannot assemble apple to the orange. That does not work. So how can you do it? Even if it's defined.
Once you have it, you adjust everything to the global coordinate?
Yes, good, thank you. So before you assemble it, you need to transform back to the global coordinate. Everybody has the same reference, U1, V1, U2, V2, U3, V3. Then now you can allow to assemble. So that's what we are going to do. Everything is all about coordinate transformation. So from local coordinate to global coordinate. before assembly. So since this is a finite element class, not your geometry class, so I will not go through too much detail about the coordinate transformation. I will just illustrate the expression at the very end. Okay? So if you have a bar, and then you have U1, V1 with the angle phi, and then you have U2, V2, right? And then you have this is my U1 bar, and this is my U2 bar. I'll go slightly different format than book. Just because I want to give you different flavors so that you can practice different ways. One, read the book, follow the format that the book presented, and then try to this way, and then see if you agree on both of them. So U1 bar is U1 cosine phi, V1 sine phi. Did I say it's a direction cosine? But there is a direction sine here, right? One is a cosine, the other one is a sine. So why we don't call it direction sine, but direction cosines?
Because phi is with the horizontal.
Phi is with respect to horizontal. If the phi is given from vertical axis, then the second term will be cosine of that phi. So this is, let's say, P2 and P1, right? Then it will be cosine P1 plus cosine P2. So that everything will be written in the cosine. But since we only use the horizontal axis reference, we have that issue. All right. Same, U2 bar, U2 cosine phi, V2 sine phi. I don't like writing cosine and sine every time, so let's define this one as L, this one M. Okay. In 3 dimension, then instead of LM, we have a L, M, and N. We have a 3 direction cosines. So just one extension of one additional dimension, so there is not much point to go through it. So that's what it is. So now I write it, this one, in terms of the matrix notation, because that's my favorite notations. So let's say U1 bar, U2 bar. Okay, in terms of U1, V1, U2, V2, right? I'll be really mad if you still don't know how to multiply matrix to vector at this point. So make sure that you practice enough. This should be L, M, 0, 0, and then 0, 0, L, M. Any questions? So I will say this is a Q bar. The displacement, nodal displacement vector U1 bar and U2 bar, we collectively call it Q bar, equal transformation matrix times Q. Dimension, this is 2 by 1, this is 2 by 4, and 4 by 1. Okay, if these dimensions are different, then you cannot multiply matrix and vector, right? So keep that in mind. In the book, I define the transformation matrix T as a 4 by 4. Okay, and I expand my element matrix 2 by 2 to 4 by 4, and then multiply by 4 by 4 matrix. But at the end, it will be the same results. Any questions? So this one says, if you give me the global displacement, I will give you local displacement, right? If you give me the global displacement, because at the matrix equation, after you assemble it, you solve it, what you have is you will have a global displacement. Now then you need to convert it to the local displacement by multiplying by this T matrix, then you get the local displacement. Force. This is displacement. Force. I have opposite relation. Okay, so I want to calculate F1x, F1y, F2x, F2y. So this is my global force. Okay. Did I say it's a two force member? So it should have an x component, right? There is no y component of force in local coordinates, right? In local coordinates. So in the global coordinate, you have an x force, y force, x force, y force for both nodes. But in local coordinate, you only have x force equal Lm 0, 0, 0, 0, Lm of your local force F1x bar, F2x bar. So I will say this F global T transpose F in local. Dimension 4 by 1, 4 by 2, and 2 by 1. Again, is satisfied the rule of matrix multiplication. I believe there is something on handwriting. So try not to read equation by your eye. Try to copy the equation on the paper. The learning experience is much better. Okay, trust me. All right, now we have all equations that we need. So let's go to original equation. Okay, equations. So original equation that we have is Ke bar Q bar equal F bar, right? So that's the equilibrium equation in local coordinate system of the element. Remember, our goal is try to write this one into the global coordinate, meaning Q bar needs to be changed to the Q, F bar needs to change to the F. Q bar, yes, this is what I have, right? This is what I have. Q bar is this one. So let's write it Q bar first. Here, K bar. Instead of Q bar, I have T Q, right? So I replace Q bar to the T times Q. Equal, give some space and write F bar. Okay, give a space. How can I convert this F bar to the F? How can I convert this F bar to the F? You cannot multiply T inverse. No, T is not square matrix, so there is no inverse of the T matrix. Any idea? You multiply T transpose, right? If you multiply T transpose, then it becomes TF. So I multiply T transpose on the left. In the matrix multiplication, you cannot multiply left and right freedom. You need to multiply exactly on the same side every time. So you need to multiply F transpose, T transpose on the left. Then this one will be F, right? Do you agree? So now I write it in the same equation using coordinate transformation, the relationship between Q and F. That this matrix, what is this matrix? Dimension. This is a 4 by 2, 2 by 2, and 2 by 4. So what's the outcome of this, the three matrix multiplication? 4 by 4, right? 4 by 4. What is the matrix? It's the same matrix, right? It's the same matrix. It's the element stiffness matrix written in what? global coordinates. Original 2 by 2 is element stiffness matrix written in element local coordinate, but now this is the same element stiffness matrix written in global coordinates. So that I call it KE without the bar, so it's a global coordinate. So now then I have final equation that is ready to assemble. KE Q equal F. So this is element equation in global coordinate. And then you assemble, you apply the boundary condition, you solve the system of equation exactly same as the one-dimensional problem. There is nothing much. Any questions? So this 2 by 2 matrix and this 4 by 4 matrix, how do you know that they have the same property? Again, the only difference is coordinate transformation, right? So the element should be they have the same property with the one-dimensional bar and the two-dimensional truss. What's the element of stiffness, by the way? What is the element of stiffness? Physically, what is it? In my view, it is nothing but a spring constant. Spring constant. Okay. So even if this is, I call it bar or truss, but in my mind, everything is spring. So this spring constant, you try to extend it. What's the stiffness of the spring? That's your K meter. K is 2 by 2. So, but my spring constant is 1. How can I convert 1 to the 2 by 2 matrix, right? So I go to, if you like the MATLAB, so the 1D bar is K1D matrix is 1, -1, -1, 1. So this is 2 by 2 matrix. Right? And then 2D bar is this 4 by 4 matrix with L and M. L and M are direction cosines that we talk about it. So the first one is 2 by 2 matrix, second one is 4 by 4 matrix. Don't try to memorize this expression. I don't remember either. Okay? So that's not the point. Understanding what the matrix means is more important. So I use the MATLAB command, EIG command, which is eigenvalue and eigenvector. So I try to calculate eigenvalue of a 2 by 2 matrix, element stiffness in local coordinate, eigenvalue and eigenvector of 4 by 4 matrix in 2D, eigenvalue and eigenvectors. I try to see what they are. Right? So now it says lambda in 2 dimensions is 0 and 2. And this one says lambda is a 4 by 4 matrix has 4 eigenvalues, 0, 0, 0, 2. So what does this 0 mean and what does this 2 mean? This 2 is your spring constant, EA over L. EA over L, that is your spring constant, that's 2. Right? What is the 0? What is the 0? In mechanics, eigenvalue 0 means free energy. You can move, I don't need energy. So everything is stored in the structure while they are deformed. It's called strain energy. Have you heard about the potential energy? Work done by applied load? These are all energy concepts, right? The energy. So it says, 1, you need energy, 2, to deform it. The first one says, no, I don't need any energy to deform it. Right? So what kind of energy that we are talking about? This one, if there is a difference between displacement, then there will be deformation, right? Deformation. Then you need stiffness, spring constant. But now, look this one. If I move from here to there, do I need any energy? Do I have any deformation? No. Of course, there is some motion, right? But let's assume this is a static problem. We don't talk about velocity and acceleration. So if you just move slowly to this point, the displacement of node 1 is not 0. Displacement of node 2 are not 0. They're just the same, right? Then you don't need any energy because there's no deformation, right? What do you call it? What do you call it? Rigid body motion. You have a rigid body motion. How you remove the rigid body motions? You fix one displacement, right? That basically you fix that zero term so that you only have a positive term to deform. Then why, in 2 dimensions, why you have 3 zeros? Why do we have 3 zeros? Did I say 0 is a rigid body motions? So 3 0 means you have 3 rigid body motions. In 1 dimension, you have 1 rigid body motions. In 2 dimensions, you have 1 rigid body motions, 2 rigid body motions, and 3 rigid body motions. 3, exactly the 3 rigid body. The only non-rigid body motion is deformation along the axial direction. All right, so this K element, the K matrix, is still have the same EA over L. Okay. You multiply T transpose K with a T, right? You do the math. I will just write the final answer. L square, LM, negative L square, negative LM. It's a 4x4 matrix. And it's a symmetry. So this one has to be LM, negative L square, and then negative LM. Here M square, negative LM, negative M square, negative LM, negative M square. L square, LM, LM, and M square. This is the element stiffness matrix in global coordinate. I will not go through assembly process. I will not go through applying the displacement boundary condition. This is trivial, so I will skip it. So let's assume you assemble them. Let's assume that you apply the boundary condition. Let's assume that you solve the problem. Then what do you have? You have global displacement Q, right? Global displacement Q. So U1, V1, U2, V2, U3, V3, U4, V4. From now on, what you need to do is you need to recover element force, the stress of the member. So element force. So how can I get the element of force from global displacement? Give me some idea. What should I do? So now you're going backward, right? From global displacement, you calculate the local displacement. Now if you have a local displacement, then you can multiply by your local K matrix, will give you a force vector F. So that's the process. You need to go back to the local coordinate. So P over element is EA over L times U2 bar minus U1 bar. How do I calculate U1 bar and U2 bar? This, right? This is basically, given Q, you multiply by T, it will give you Q bar, that's Q bar. Or if you don't, you skip the one step, then the shortcut will be EA over L. Instead of U2 bar, you just directly calculate LU2 MV2 minus LU1 MV1. You can do that too. I don't mind either way that you do it. But conceptually, I want you to understand that I need to recover local displacement and then multiply by stiffness matrix to get my element of force. Stress. This is a two-force member, so you only have axial component of the stress. The sigma over E equal PE over A. Same sign. Okay, so if stress is positive, PE is positive. Stress is negative, PE is negative, right? So this PE, it's unfair to call it force. Even if I say it's element of force, it is unfair to say, because force is a vector, so it's a positive direction and negative direction depending on what coordinate system do you use. But this is more like resultant. It's an integral of the stress. Okay, so what is the positive stress mean? Tensions, right? Tension. So that the one end goes to positive, the other end goes to negative. The tension. The PE is positive when element is in tension. PE is negative when element is in compression. Any questions?
What do you mean by same sign when you write same
Sign. If PE and sigma are the same sign. If sigma is positive, PE is positive. If sigma is negative, PE is negative. That's what I mean. What does this is called a linear problem. What does the linear means to you? What does the linear means to you? So let's say if I apply 1 Newton and then it gives me displacement of 1 inch. I apply 1 Newton and solve the problem, it will give me 1 inch of displacement, right? Then what if I apply 2 Newton? The displacement will be 2 inch. Okay, so now if I change the force, do I need to solve the problem every time at different force? No, you need to only solve one force, right? And then you change the force, then your displacement will follow exactly the same pattern. When it's useful, let's say you are trying to do fatigue analysis. Do you know fatigue analysis? You have the loads coming as time history, then you don't have to solve the finite element every time step. You just solve a 1 Newton displacement, and when you apply force, then you multiply that magnitude to your displacement, then you are done. So that's called method of superposition. Superposition is, in my view, the most important property of the linear problem. You can superpose your result for different combination of force, whatever that you want. All right, that's all for today. Thank you.